Day 121 notes pre-calculus. Today we move into a new unit in our class, and this unit covers trigonometry. We're starting with chapter 6.2, and we're going to look at the trigonometry of right triangles. Now it's important to remember that right triangles are pretty helpful to us, especially if those two right triangles are similar in shape. Now similar means that they're the same shape but a different size. Because the reason why this is particularly helpful is that their side lengths are proportional to one another. Now the reason why this is particularly helpful is because these smaller right triangles are great substitutes for dimensioning large objects. For example, if I have a picture of, let's say, a building that I need to identify the height of, if I knew that the height of that building in this picture was 3 units tall and there was a particular length along the ground that I can measure that was 4 units wide, so in this picture it was 3 units tall and 4 units wide. If I go to the real world and measure along the base of that object to be 8 units wide, I could then identify the missing length here, the height of that real object. And so if we were to set up a proportion, it might look something like this. 4 divided by 8 equal to 3 divided by our question mark. The thing to remember when setting up proportions is that you always have to set up the proportion in the same direction. So if I'm using 4 over top of 8, in this case, 4 over 8, left triangle over the right triangle, I have to use the same direction here when I use the other dimension, 3 over our question mark. Now when it comes to solving these proportions, hopefully you remember that you can cross multiply and then divide by the third value in the group, and that will identify your unknown. Now in this case, 3 times 8 is 24. 24 divided by 4 is 6. So if this object was 3 units tall and 4 units wide, its substitute in the larger dimension would be 8 units wide and 6 units tall. Now we could be talking about inches here on this model and then feet in this model, or even miles for that matter. The proportion will hold true regardless of what our units are. And that again is particularly helpful for us when we're dealing with large objects that are difficult to measure. For example, if I need to know the height of the Eiffel Tower, I'm unable to climb to the height of this object. It's very difficult to climb that. Plus, it'd be surprising if I had a measuring tape long enough to reach that. However, if I can determine that the length of its shadow at a particular time of the day is 500 feet, and I have a broomstick sitting next to it that's 5 feet tall that casts a 2'4" shadow, I could then use proportions to find the height of the Eiffel Tower. Now this is going to be x, my unknown. I might write the fraction x over 5 because I'm comparing one height to the other height, x over 5. That would have to be equal to 500 over 2'4". Now I know that 2'4" is the same as 2 feet and 4/12 of a foot, or in other words 2 1/3 feet. Now I can use the fraction or I can use the decimal approximation, 2.333 repeating. Any of that would be fine for this calculation here. Now as far as solving it goes, we need to cross multiply, so multiply across the diagonal of the two values that are known and then divide by the third number that exists. So we'll multiply 500 times 5 and then divide by 2.3 repeating. And I'll just punch that in a bunch of times here. This comes up to 1071.4286. 1071.4286 feet. And that would be a pretty good approximation. I think the actual Eiffel Tower is 1,063 feet, if I'm not mistaken. So again, pretty good approximation using the pieces that we know. Now, pictures of triangles or adjacent objects are nice. So if I had, again, a picture of a rectangle, I can measure it and use that to represent the real-life object. Or if I have two real-life objects next to one another, that's nice to work with. However, we can also determine these dimensions by using our trigonometric ratios. Now, in order to use trigonometric ratios, we have to identify the parts of a right triangle. First things first, every right triangle has a right angle down in the corner here. Also, every right triangle has at least one angle of intention, or one other angle that we're focusing on. And in this case, that angle is placed right here in this corner. This angle, we don't know the angle measure of it, so we're going to call it theta. A lot of times we use Greek letters to represent unknown angle measures, since we use regular letters to represent side lengths. Now, this angle, being a right angle, is 90 degrees, and this angle has to be something less than 90 degrees, since all three angles together can only add up to 180. But back to describing the right triangle itself, relative to this particular angle here, we can identify two of our side lengths. Now, the side that's directly opposite of this angle we call the opposite side, and the side that's directly next to this angle but not the hypotenuse we call the adjacent. The hypotenuse is always the side that's directly across from the 90-degree angle. You might also remember that the hypotenuse is always the longest side of any right triangle. Now, if our angle of intention, or the angle of focus, happened to be up here instead, then the names of these sides will change, because now the side length across from our angle of intention is down here, and that would be the opposite angle. The angle next to, or nearest to, this angle is here, so that makes this our adjacent angle, but in this case our hypotenuse did not change. This is still representative of our longest side, and it is still opposite or across from the right angle. So it's important to notice, or to note, that these sides can change depending on what our angle of intention is. Now, you might be familiar with the three common trigonometric ratios: sine, cosine, and tangent, but you may not be as familiar with cosecant, secant, and cotangent. And that's what we're going to work on here as we move forward. The sine function creates a ratio between the opposite side, opposite of our angle of intention, and the hypotenuse of the right triangle, whereas the cosine function creates a ratio between our adjacent side and the hypotenuse, and the tangent function creates the relationship between the opposite and adjacent. These are the three different ways that we can create relationships or ratios between the three different sides: hypotenuse, adjacent, and opposite. If I were to flip these fractions, or if I found the inverse of these fractions, then that would produce the functions below. So the inverse of sine is cosecant. Instead of a ratio of the opposite side length divided by the hypotenuse, we're now looking at the ratio between the hypotenuse divided by the opposite side. Or cosecant, cosine, the inverse of cosine is secant. And lastly, the inverse of tangent, or the opposite of tangent, is what we call cotangent. So these are the 6 trigonometric ratios you should be able to identify given information for a right triangle. So let's go ahead and work through these. If I have a right triangle here with dimensions 3, 2, and the square root of 5, I would ask you to find the 6 trigonometric ratios of angle theta. So angle theta is our angle of intention. It's down here in this corner. The side length closest to it, but not the hypotenuse, is our adjacent side. The side length across from that is our opposite side, and the side length across from our right triangle, or in other words, the longest side, is the hypotenuse. So I said that right, but I wrote it wrong. Hypotenuse. As long as we identify each of these three sides, we should be able to identify the relationship or the ratio created for each of these trigonometric ratios. By definition, sine is equal to the opposite over hypotenuse. So the opposite side was 2, and we write that over the hypotenuse, which was 3. So sine of theta is 2/3. Cosecant of theta, which is the opposite or inverse of sine, would simply be 3/2. Cosine, as defined as adjacent over the hypotenuse, must be the square root of 5 divided by 3, since that's our adjacent side, divided by the hypotenuse. Secant is the inverse of that, so we have now 3 divided by the square root of 5. Tangent, which is opposite divided by adjacent, the opposite side length 2 divided by the adjacent side length, which is the square root of 5, would yield a cotangent as the square root of 5 divided by 2. It's just the inverse of the function or the ratio above. We've now found the 6 trigonometric ratios of this angle theta. In example 2 from 6.2, we're told that cosine of alpha, this is another Greek letter to represent an unknown angle. If cosine of alpha is equal to 3/4, sketch a right triangle with acute angle alpha and find the other 5 trigonometric ratios. So I'm going to start off by drawing a right triangle, and I'm just going to label a corner for alpha. This alpha value here, we're told that cosine of alpha, whoops, I should have changed all of these. There we go, that looks a little bit better. We can now find sine of alpha, cosecant, secant, tangent, and cotangent of alpha. Now, again, we were told immediately that cosine of alpha was 3/4. So cosine of alpha was 3/4. Then we know secant of alpha must be 4/3. We know that that relationship exists between these two sides. Now, we should identify our side lengths here. This would have to be our hypotenuse in our drawing. This would be our adjacent side, and this would be our opposite side. So if cosine of alpha is 3/4, and cosine is described as adjacent over hypotenuse, then I know that the adjacent side length is 4 itself. So this is 4. Oops, I'm sorry, I said that wrong. The adjacent over hypotenuse, this is 3/4. Our hypotenuse is 4. Our adjacent side is 3. Now the problem is we don't know what our opposite side length is. And in order to find that, we have to rely on yet another function associated with right triangles, and that's the Pythagorean theorem. The equation associated with the Pythagorean theorem is a squared plus b squared equals c squared. And this says that the square of two right triangle legs is equal to the hypotenuse length squared. So one side is going to be 3 squared. The other side length, which represents a leg, is unknown. That's our b squared. And our hypotenuse c is going to be 4 squared. So 9 plus b squared is equal to 16. B squared is equal to 5. B itself must be equal to the square root of 5. And notice I'm not including a negative sign here. There is no way for a side length to be a negative length, so I'm going to indicate the opposite side as the square root of 5 only. This should make it pretty easy for us to fill in the rest of the trigonometric ratios. Sine of alpha must be the opposite side over the hypotenuse, so this is square root 5 divided by 4. Therefore, cosecant is 4 divided by square root of 5. And tangent of alpha is our opposite side divided by adjacent, square root 5 divided by 3. And our cotangent would be 3 divided by square root 5. The definition of our trigonometric ratios is very, very important. You'll hear me rattling these off very quickly, and hopefully you can do the same. If you can't, then you need to spend your time really focusing on these trig ratios. Start by looking at the 3 standard trig ratios, and then recognize how those can be transformed into our secondary trigonometric ratios. Another type of problem that you'll see this week as we move forward is a problem asking us to solve the triangle. Now, solving a triangle simply means to identify the side lengths for A and B in a right triangle if we have at least one angle measure given to us. Now, using this angle measure, I'm going to think of my trigonometric ratios, and I'm going to start by solving for lowercase a. Now, in this case, this is an opposite side, and the other numeric value that's given to us is a hypotenuse. So if I think of the trigonometric ratios that include opposite and hypotenuse, that's either sine or cosecant. Now, I'm more familiar with the original trigonometric function, so I'm going to use sine here. I know that sine of our angle measure, 30 degrees, must be equal to the opposite side divided by the hypotenuse. Now I can go to my calculator and evaluate what sine of 30 is. I'll do that in just a moment. I would like to get a by itself first, and I'll do that by multiplying both sides by 12. This way I only need to go to the calculator one time, 12 times sine of 30 degrees, and that would tell me what a is. And so on my calculator, if I have the number 12 times sine of 30, to pull our sine calculation up, I'll click the trigonometric button here. So trig button, and I'll click on sine, and inside I'll write the number 30. I can press enter, and I see that my result here is 6. The side length for A must be 6 units. So that's part of my solution. Next, I need to find the side length of B. Now, B is what we would call an adjacent side compared to this function. And the 2 trigonometric ratios that deal with adjacent side lengths and hypotenuses is the cosine function or the secant function. Now, I'm more familiar with the cosine function, as you might be, so I know that the cosine of 30, cosine of our angle measure, must be equal to the adjacent side divided by the hypotenuse. And in much the same fashion, if I multiply both sides by 12, that will isolate the value for B, and we see that the side length B is equal to 12 times cosine of 30 degrees. So on my calculator here, 12 times cosine of 30 is equal to 6 times the square root of 3. B is equal to 6 times the square root of 3. Now, if you're using a handheld calculator that doesn't give precise results, that's okay. If you see the result 10.3923, that would be perfectly fine to use. Just make sure that you round it appropriately to the 4th decimal place. 10.3923, and either of those solutions would be correct. Now, solving the triangle generally means finding the side lengths that are missing from the triangle, but it's also good habit to get into to find the missing angle measure as well. And this one's easy to do. The missing angle measure here must be 60 degrees because the 30 degrees plus 60 plus this 90 adds up to 180. So as far as solving the triangle ABC, I think we've got a pretty good solution. We have our two missing side lengths and our missing angle. We know all three angles and all three sides. We're going to finish out this video with two examples, two more real world examples. In this example number 4, a giant redwood tree casts a shadow that's 532 feet long. So we have a shadow that's along the ground here at 532 feet. Find the height of the tree if the angle of elevation of the sun is 25.7 degrees. So if I'm looking at the sun here, it's shining its rays down away from it, and it looks like the angle between this sun and the top of the tree is 25.7 degrees. Our job is to find out the height, the total height of that tree. Now this is called angle of elevation because the angle measure is increasing as we approach our target here. It would be called an angle of depression if the triangle was upside down, if we had to measure downward from our horizontal position. But we don't have that here. We've got an angle of elevation, so we can calculate this result here. Now, according to this angle measure that's known, we have a hypotenuse. I'm sorry, not a hypotenuse. We have an opposite side. This one over here is opposite, and this is adjacent to the angle. So the two rules that deal with opposite and adjacent are cotangent and tangent. Now, in terms of our tangent argument goes, we know the tangent of our angle measure, 25.7 degrees, must be equal to the opposite side over the adjacent. So opposite side is our unknown h divided by the adjacent side, 532. If I multiply both sides by 532, that will solve for h. So when I look at the calculation here, 532 times tangent of 25.7. So it looks like the height of this tree is 256 feet. We'll just go ahead and round that to a whole number here, 256 feet. Now it is important to know that we can use the cotangent function here as well. Cotangent of 25.7, instead of being opposite over adjacent, would be adjacent over the opposite. And so the way we would solve this is we would move h to the other side of the equation, and we'd move this entire piece, cotangent of 25.7, to the denominator of this fraction. That's the algebra shortcut I was talking about last week and a few other examples. We have cotangent of 25.7 now in our denominator. So if I have a fraction 532, let me go back to this. I forgot to write that down. 532 divided by the cotangent, so we have cotangent here, of 25.7. That result comes out to be the exact same thing, 256 feet. Height is equal to 256 feet. Either approach would be perfectly fine. Now it would probably be less likely for us to use cotangent here, since that produced our variable, or that put our variable in the denominator. We sometimes forget this method in order to solve for h. So tangent would have been more appropriate here. However, if we knew what h was and we needed to know the length of this shadow, that unknown probably could have used the cotangent here, and the calculation would have been a little bit more straightforward. Let's see one final example. From a point on the ground 500 feet from the base of a building, so we know that we're 500 feet from this building. So I can't seem to draw a straight line here, but that'll have to do. We are 500 feet from the base of a building. we see that the angle of elevation to the top of the building is 24 degrees. So this angle of elevation is 24 degrees. And the angle of elevation to the top of the flagpole is 27 degrees. So that's 24 to here. This is 27 to there. Find the height of the building. So h, the height of the building, and L, the length of the flagpole. Now the thing to recognize here is the length of the flagpole is only this portion of the diagram. Let's start off by finding h. We have an adjacent measure and an opposite measure, so it looks like tangent would be appropriate here. Tangent of 24 degrees would be equal to h divided by 500. And therefore 500 times the tangent of 24 degrees should be equal to h. And h can be found 500 times tangent of 24 degrees. So let's go ahead and find the precise result there, or at least a decimal result, 222.6 feet. 222.6 feet. Okay, that's the height of the building. Now our job is to find out what the length of the flagpole is, and it might be pretty difficult for us to figure that out. There's a difference of 3 degrees between these two triangles, but the problem is if I start focusing on that 3-degree difference, I'm no longer working with a right triangle anymore. So that voids, or that eliminates our ability to work with the 6 trigonometric ratios. So what I might do instead is consider this right triangle next. Find the total height, maybe call that h2, the total height, and then subtract the 2. When I subtract h2 with this original h, that's going to tell me what our length was left over. So the approach here is very similar. Tangent of 27 this time must be equal to our h divided by 500. So if I reuse the calculation from before, 500 times tangent of 27 instead of 24, then I see that that height is 254.8 feet. 254.8 feet. Now to subtract the 254.8 minus 222.6, 254.8 minus 222.6 leaves me with a height of about 32.2 feet. So L, the length of our flagpole, let's put this in a different color. L was equal to 254.8 minus 222.6, and we have a total height of 32.2 feet. So I apologize for the very long video if you ended up having to watch this video for missing class or us not having class on Monday. Hopefully some of this was a review to you and not brand new for the very first time. If this was brand new to you for the very first time, then I really need you to focus on and study these trigonometric ratios and understand that these are the definition of these trig functions. Sine, cosine, and tangent are the most important to start with. If you do anything over the next 24 hours, you need to study and ensure that you know that sine of an angle is the opposite over the hypotenuse, cosine is the adjacent side length over the hypotenuse, and tangent is equal to the opposite side length divided by adjacent. Start with that and then begin applying those ratios to each of these practice problems below. If this is a review for you and you've seen all of this before, then please make sure that you're comfortable with each of these different types of calculations. We can use proportions in right triangles. We can use the trig ratios and identify the ratios. We can use the Pythagorean theorem to find missing side lengths of a right triangle. we can solve a right triangle by finding all side lengths and missing angle measures, and then we can start to apply these rules to real-world problems as well.